So other things, you cannot buy a quart of Pepsi. It is a liter, 2 liters, 3 liters, same with water. So our larger volumes of fluids are metric. Photography has always been metric. 70 millimeter film, 35 millimeter film, 50 millimeter lens. Our nutrition labels are metric. How many grams of sugar is in that product? How many grams of salt? How many calories? These are metric units. And one of the last things I thought would ever switch over is engine displacement. It went from cubic inches to liters. Nobody even told us that they were doing that. They just did it. And now we speak fluently in liter displacement of our engines. And so it's slow, but there's some I'm holding on to. I'm not giving up. I'm keeping my dozen eggs. And I'm not renaming the inchworm. And I'm still calling it footage of a film. Footage. What footage did you get? I'm not saying meterage. And I still kind of like my Fahrenheit. Oh, it's in the 30s today. It's in the 40s today. It's in the 50s or 60s. Each of those is a kind of comfort zone that we're tuned to. And in metric, they don't really have that in Celsius. Are you in the upper third of the next 10? I'm sure they're happy with their Celsius. Why am I talking about all this? For no reason. I was just distracted. Back to a new density that I just made up called thimble density, okay? So, we have a kind of dead star called a white dwarf, and if you take 1 thimble of its material, it will weigh 1 ton. Okay? And it turns out a metric ton is about the same as like an English ton, so we don't have to specify here. So, 1 ton per thimble. And that's pretty heavy, but it's not the heaviest we've got out there. A neutron star is 1 trillion tons per thimble. That is the densest matter we know. And that is the death of a high-mass star. And if I'm going to forge Moonyear, the name of Thor's hammer, I'm going to do it in the baddest ass star I can possibly find. A neutron star. So, I proceed. And then I tweet about it. So here it is. If Thor's hammer is made of neutron star matter, implied by legend, that it weighs as much as a herd of 30 billion elephants. Now, how do I know how big Thor's hammer is? Thor was kind enough to lend me the hammer so that I could make the proper measurements. Okay, so you think that's a geeky thing to do, don't you? You feel it. I know you're thinking. This guy Tyson is geekier than we ever imagined. But I do not wear the crown of the geeks. That would go to others who walk this earth. Sorry, Neil Tyson, but you're wrong about Thor's hammer. Material scientist, North Carolina State University. Okay, that's Matt on the left, and that's Suveen on the right, holding Captain America's shield. The critical mistake, Tyson, we are arguing about Thor's hammer. The critical mistake Tyson makes is thinking that Mjolnir was forged off the core of a dying star, when it was actually forged in the core of a dying star. Program manager of the Material Science Division of the U.S. Army Research Office. Your tax money at work, right there. An adjunct material science professor at NC State and diehard comics enthusiast. It's well documented that the hammer is made out of Uru, Thor's native realm of Asgard. And he can cite documentary sources to back him up. For example, Marvel, which publishes the Thor comics, issued a Thor's Hammer trading card in 1991 that states Mjolnir is made of Uru and weighs precisely 42.3 pounds. Who likes my answer better? No, I'll give it to him. Of course, this is accurate. But I had fun giving an awesome wrong answer for that hammer. So clearly then it's not how heavy it is. It's whether you have this spirit energy from Asgard to lift it. So, however, something they do not, if it only weighs 42 pounds and it drops to Earth, it would not make a crater half a mile across. But 300 billion elephants would. Mathematics. By the way, no movie is spared in this talk. Okay? No movie is spared. Let me ask my 8-year-old friend here, have you seen this movie? Yeah, of course, everybody's seen this movie. Did you like this movie? It didn't scare you? Okay, oh, he said no, of course not. Okay, every grown-up here, when they saw the flying monkeys, they freaked out. Am I lying? Okay, did you know there's mathematics in The Wizard of Oz? Let's listen. Ready? Okay, which one of them does not have a brain? Scarecrow, okay. After this scene, in spite of what he thinks, he still doesn't have a brain.
Everybody can have a brain. That's a very mediocre commodity. Every pusillanimous creature that crawls on the earth or slinks through slimy seas has a brain. Back where I come from, we have universities, seats of great learning, where men go to become great thinkers. And when they come out, they think deep thoughts, and with no more brains than you have. But they have one thing you haven't got, a diploma. Therefore, by virtue of the authority vested in me by the Universitatis Comitiatum e Pluribus Unum, I hereby confer upon you the honorary degree of PhD. PhD? That's Doctor of Thinkology. Some of the square roots of any two sides of an isosceles triangle is equal to the square root of the remaining side. Oh, John, I've got a brain.
Apparently you really still don't. Okay, here's what he uttered. The sum of the square roots of any two sides of an isosceles triangle is equal to the square root of the remaining side. Now, when I first saw this film, I did not know trigonometry. And I longed for the day that I could walk out of a trigonometry class and then understand what he said in that scene. So the day I understood it, and then re-listened to that scene, I was so disappointed. Because I was just a kid, and these are grown-ups writing this movie and making this movie, and how much would it have taken to just check this with the local math department? So here's what he said. Sum the square, that's not it. If he said it correctly, because he's really reciting what? The Pythagorean theorem, and this is the Pythagorean theorem. The sum of the squares of the two legs of a right triangle is equal to the square of the remaining side. So these are not even kind of sort of like each other. It's not like he messed up a couple of the words and he gave it to him because there's a lot of words in a movie and maybe you remember. This is wrong. It's just wrong. And here is Pythagoras. I guess he looked like that. 500 BC. Here's our right triangle. I should have put a little right angle thing here between A and B. So A squared, the length of A squared times B squared equals C squared. Pythagoras. You learned that in what, 7th grade? not quite elementary school. So there was their attempt at the Pythagorean theorem, and they botched it. But everything else about that film was real.
There's loose on the ground.
We'll get through this, I promise. We're going to like Frozen. I was kind of indifferent, you know. It was all right. And what were those little... Oh, someone said, let it go. That's very cute. Very cute. I get it. What were those rocks that came to life and rolled and then... Trolls! They look like rocks. Okay, trolls. What was the point of that scene? She can't answer that. Okay, fun. Here we are. We are lifting ice. The movie opens with singing ice cutters. And I want to call to your attention that in later years, Disney clearly has scientifically literate people in their offices, because ice, we all know ice floats. Most people, if you say, draw a floating ice cube, they will draw it like a floating cork, with most of the ice cube just sitting up on top. Because when you think of floating, you think of floating. You don't think of something that has only a little bit of it floating. You think of it, most of it is floating. Ice floats with only 10% of its volume sticking above the water. They knew this when they drew the scene. So when they pull the ice cubes out, that's how big they are. And I measured this, and it's basically a tenth of the volume. Okay? This is why icebergs are hiding most of what they are. This is what makes icebergs especially deadly for ships, such as Titanic, which we will visit later. Frozen water, you take H2O and freeze it, it's a density issue. It becomes less dense than water and it floats. A profound fact in the history of life on Earth, because most things, when you cool them, shrink and become more dense, and then sink. Ice, when you shrink it, it becomes less dense and floats. Which means in the winter, as you freeze a lake, the upper surface freezes, but it does not go to the bottom. It stays there, insulating the water below from the cold air above, thereby not freezing to death every single fish in a lake. It's how aquatic life survives the winter in all the major bodies of water that freeze over the winter. So this is not just a simple fact, it's a profound fact. And if you squeeze, this is also why your pipes break in the winter. The water freezes if you left water in them. It's also why you can ice skate. You skate on ice not because the ice is slippery. You skate on ice because the pressure is squeezing the ice to less than 10% of that extra volume. It cannot stay solid if you squeeze it to less than that volume. It will instantly liquefy, returning to the state of matter from which it came. So that as you skate over ice, you are melting a bead of water under your blade, and you're gliding on water, on the ice, not on ice. And it's all traces to this act. So now, that's not even why I'm taking you to this movie. That's a trivial point, which is where the ice floats. Let's get to the action here. Ready? Ice person here is ready to do her thing. Ready? Here she goes.